Let us start the lecture number 2 of this module, that is module number 5. In the previous lecture, we analyzed the various harmonic component, both your AC and DC side, and that was for the ideal case. We assume the overlap angle is 0, but in the practice overlap cannot be 0. It is normally some significant value, sometimes it is a 5 to 20 degree. So, the impact of this U is also very significant in the harmonics. As U increases, because we took U is equal to 0, and if U is increasing from 0, the magnitude of harmonics decreases, but the higher order harmonics magnitude decreases more rapidly than the low order harmonics. Basically, all these analyses are based on the various studies, various reports, and here then measurements. People have summarized this, so here I am also summarizing here. So, we are not going to analyze the individual, but this is the summary gist of the various studies. So, once U is increasing, it says the magnitude of harmonics decreases, but the higher order harmonics decrease is more rapidly than your low order harmonics. The rate of reduction of harmonics increases as U increases up to a certain limit. So, it is basically increasing. If U is having certain limit, then this reduction of rate of reduction increases very high value. It also said that each harmonics decreases to a minimum at an angle U is equal to 2 pi upon h. H is your components, means h is your 5th, 7th, 13th and 11th. This once you are reaching this U at this value for, let us suppose once your U is here, h is your 5, then 2 pi upon 5, then this component is basically decreases to its minimum value. So, if it is a for 7, then it is a 2, if U is this, then the 7th harmonics is the minimum value. When U is held constant, because there is possibility that we are varying alpha is an intentional vary, because we want to change the voltage and we are just delaying this angle alpha as well as the beta, you can say, in the inverter circuit. But this U depends upon your circuit and other network conditions. So, if this is a constant and you are delaying this, you are changing basically this, then the impact of harmonics magnitude as well as its contents is very, very negligible. Why it is so? You can see here, if you will see, this is your current, this is a 120 degree, this is 60 here. If you are delaying here in the ideal case, so only this is the shifting. So, the magnitude will be the same, only this here, your axis here, the phase shift will be there, nothing else. But you are taking this U here, that is going, then the impact will be there, but it is very, very small if your U is shifting. It is also said that for a given current means I am talking about the DC current. For a given DC current, when alpha is increased, means for a larger alpha and U is less, decrease, then harmonics tends to increase and the reached is highest value as is equal to 0. So, these are the basically 5 summaries when alpha and U are changing. This is true for your rectifier circuit, is true for your inverter circuit as well. But the major components, that is coming your 5th, 7th, etc., those will be there and they will share the highest, most of the current characteristic harmonics will be the highest in that 5th, 7th, etc., that is characterized by your NP plus minus 1. So, the component here of this order of harmonics will be larger and it will be there only the slight change in the magnitude once your U and alpha is changing. And some more components will arise if your U is here significant, because then we are going to have other than these harmonics in your AC system, and that is called your uncharacteristic harmonics. Now, to filter out, because we saw your harmonics component here, it is basically if it is your fundamental component, then it is your H is harmonics. So, your IS current in AC side, it will be the fundamental component divided by that harmonics component. And now you can see if it is this H is low, this value is larger, and if it is H is higher, this component value is very less. So, we should not worry about that, it can be allowed to enter into your AC system. So, here we want to filter out some of the harmonics that should not, because its magnitude is significant, so it should not enter to your AC system. So what we do, we use the filters, and those are called harmonic filter. So the purpose of harmonic filters are to reduce the harmonics voltage and current in AC power network, and also it provides some reactive power support at that AC bus. We will see if you are designing a filter for any harmonics, and for that harmonics it will provide the minimum impedance, but for the fundamental component it will provide the reactive power support. I mean to say, if you are using your this shunt filter, here it is your RLC circuit, this is a shunt filter, here at particular harmonics, what will happen, this L and C impedances will be vanished and will have only impedance here. So for that it will give the minimum impedance. But for same circuit, if the frequency is your F, that is a fundamental frequency, this circuit will behave like a capacitive circuit, and means it will provide the reactive power support, and we need it. In converter stations we require huge reactive power supports, so some of the reactive power support is provided by filters itself, and the rating sometimes is denoted by the filter rating, is how much reactive power it will provide at the fundamental frequency. No doubt its rating is for which frequency it is providing the minimum pass, let's suppose 5th tune filter or 7th tune filter, and also at the same time how much MVA or it is giving at the fundamental component. So the main purpose here is to no doubt to reduce the harmonic current as well as the voltage that is entering to your AC system, or if it is going the DC side, the DC system, but in AC system it provides some reactive power support at the fundamental component that is required. Now the various type of filters are proposed, and in theory and in also in the application various type of filters are there, and we can categorize those filters based on the certain criteria, and the first criteria is based on the location. So your HVDC system, if you again this is your converter transformer, this is your AC system, we are having here rectifier, this is your link. So if your filters are AC side, it is called AC filters. If you are using the filter the DC side, it's called the DC filters as usual. So the AC side, basically we use the primary side of here. Now the question is, we can use, this is your 3-phase going, we can use the filter here, we can use the filter here.
Voltage difference?
Yeah, it depends on the what is, if it is a unity turn ratio, so you can put here as well as here. But normally what we do in the practice, we put the filters here rather than here, because here this OLTC is changing, online tap changers are changing here, and thereby that may create some other problems to the system. So we always try to put your filters, that is the AC side, on the primary side of the transformer. Not only for this region, let's suppose this is your star star. If you are using another system here, that is your star delta, then some of the component will be cancelled to each other. Otherwise what you are doing here, putting the filter for all 7th, 5th and 7th and 11th and 13th, here you are also putting for that, but that is not required because here it is not going, they are cancelling each other. So we put here, that's why it is written, it is a primary side never connected to the valve side. Valve side means this side. We put the primary side of the transformer. Sometimes also we use the tertiary winding of this, because the voltage of this bus is very high. Normally it is 400 kV AC system. This is a 400, and if it is coming this side, maybe it is depending on if we are operating here the plus minus 500, the voltage will be calculated here, what will be the voltage. So this 400 voltage is very, very high. So what we do, we cannot connect a filter at the 400 kV. It is very expensive because you require the insulation level of that voltage, and your inductor, capacitor and resistor size will be very, very uninsulated properly. So what we do, another option that we can use a tertiary winding of this transformer. Even though here if you are putting in the primary side, this will be through some transformers, and then you can put the filter. So then you are incurring extra cost here, because from 400 you are going to maybe 66 kV or 33 kV, and then you are connecting the shunt filters there. So if it is used here the filter in the tertiary winding, because the voltage is low, so you are minimizing the cost compared to this transformer. No doubt if you are adding another winding, the cost will be more. Another problem here, you are increasing the impedance, because here the L value is going to be higher. If you are using a tertiary winding, that leakage flux is also coming here into the picture, and effectively the reactance is going to high. So that's why it is written the tertiary winding. It is no doubt the low voltage we are getting through the tertiary winding, and the cost will be less compared to this transformer. No doubt we are putting extra winding, extra cost will be there, but I am comparing the 2 winding transformer and this 2 winding transformer, then compared to a 3 winding transformer. So this cost will be less, but here the impedance of the tertiary winding will increase, and we are getting U will be more in that case. So another is the DC side, because this side we are getting the AC current harmonics, here we are getting the DC voltage harmonics. So we put the filters as usual, and that filter is nothing but your smoothing reactors. We put the smoothing reactor this side, and that's why the DC reactors are put. Sometimes we also put here some reactors here in the shunt also for the voltage, because the current here we want the smoothing reactor to make the current constant, ripple to be minimized. But some of the harmonics it should not travel, because the harmonics may cause extra loss. So we can put some here filters that harmonics can be damped out through the resistors, and it should not flow in the transmission line. Because if this is happening here, that is not a utilized power, and the loading of the line will be more. So we can filter it out without any problem. So we use here again the reactors. If we use the reactors, it will be going down. So that's why the DC side we use the reactors. Now another criteria is based on the type of connection. Here every time I am showing, this is just like a shunt. So based on the connection, we can say our filters can be categorized, or you can say classified into the 2 types. One is your series type, another is your shunt type. Series type as usual. Here this is your inductor, this will be a capacitor, and this is put in the line. So if you are putting here, this is your series. This side also you can put here in the each lines. These filters, what happens, they basically provide the, if any harmonics component entering here, the combination will provide the infinite path. It will just behave like an open circuit. So it will not enter to your AC system. So this is a series here, just like open circuit, but the fundamental component, it will provide some reactance, but it will be not the open circuit, it will be minimum outputs. So this is your series filter. And series filters basically normally in HVDC they are not used. They are used only one filter here we use for the smoothing reactors, that is in series. But in AC side we prefer to use the series shunt filters, because it has several merits. So compared with the here series and shunt, the shunt filters are cheap compared to your series filters. The reason here, because already here it is written, the series filters carries full current and must be insulated for full voltage to the ground, because if you are putting here in the line, this inductance must be insulated properly through the ground. This inductor is not hanging in the air, mind it. It will be, the inductor will be on the ground, because wire cannot sustain. This is the inductor, means just like a transformer, air core transformer is a huge inductor. So it will be on the ground, only just we are making connection here. Means this is your inductor, this 2 terminal will be basically coming here and here. The electrically I am just representing as an inductor here, but it is not hanging in this air. It will be here. So this is a huge voltage inductor, so it must be insulated from the ground. So full voltage is appearing here. This is a 400 kV line, 400 voltage must be insulated. Another here, through this path we are flowing the full current. Now you can imagine the current which is flowing in the kiloamperes. So here the kiloamperes is current flowing through this. So use the rating of these coils and the capacitors here, it will be very, very high, and that's why the cost is very high. Now as compared to your shunt filters, here this is a shunt filter, this is carrying the harmonics component current. No doubt some current will flow at the fundamental frequency as well, because this is some impedance is offered. But for this fundamental component, the impedance here will be larger. It will be large enough. The impedance offered for which it is tuned, it will be the minimum, because this is cancel each other impedances, only we are having the resistance. So, and that current is flowing only the harmonics component, and that component here is basically this by H. So, this is sustaining the less current, and thereby here this is the chip, and it is containing the full current. So, that is why here I have written the series filter carry full current, series filters carry full current and must be insulated from the full voltage to ground. The shunt filter carries a small amount of current plus some fundamental amount of current, means no doubt it is that is designed for IH, means harmonics component current, plus it will be flowing some IF plus also some other components. But the highest here which will be the flowing here, that is if you take the RMS value here I, the I which is flowing in the filter will be your I1 square plus your, here I can say summation of IH squares. But for which it is designed, that component will be the significant, another component will be again less. So, basically it is carrying this amount IH in this. And the better here I can say the best advantage here, that the shunt filters supply the reactive power at the fundamental frequency, whereas the series filter consume it. Now, means this effectively for the fundamental component, suppose it is designed that it will offer the open circuit for certain component. Let us suppose I am saying our fifth harmonics current I5 should not flow, means the impedance here will be in such a way that the fifth component, it will be here impedance will be infinite, the effective impedance. So, what happens here, and if you are calculating this, what will be your I1 here, means a value of total effective impedance at the fundamental component, here it will be inductive, means it will consume, that is consuming here, that is whatever I square into this, what will be your effective value. So, this reactive power it is consuming, here it will be generating, and we need it, the best option that we require this reactive power generation. We do not want that it should consume, because then we require more reactive power support at the converter stations. So, this is the best option, that is why we always use the shunt filters at the converter station. Now, the shunt filters here, since this is here the phase to ground, so we can have the combination of the star connections or we can have the delta connections, means this three phases are there here. So, three phases can be connected here in your like this, or we can have the three from here to ground, here to ground, here to ground. Then you are having the ground. So, what we do normally, we add the grounding part here and we can have this three way. So, either it can be star or it can be delta, but it is again preferred the delta, star is the preferred. However, the series filters, there is no option, you cannot have the delta and star, it is the phase wise, so it will be the phase connections. So, single this phase, then we will have the similar another phase here for A, here for B, and then we have the for the C as well. So, they are the in the phase. This point number here is this is the fourth point. We will analyze this and we will see really it is giving reactive power, means this whole becomes capacitive when we are just operating at the fundamental frequency. If it is for fundamental frequency, we will see the value of this. Another is based on your sharpness of tuning, and you know there is the two type of filters are classified in this. One is called the tune filters. Tune filters, normally it is limited for 1 and 2, means we can go for single tune filters, we can go for the double tune filters. And another is your damped filter, or sometimes called the high pass filters. The tune filters are basically has a high quality. The quality factor means it is defined with the inductor and capacitor values, as a quality is normal quality just. And here only one inductor is subjected to the full line impulse voltage. I mean to say, if you are using here, this is a tune filter. In this tune filter, this is one inductor here which is sustaining the full voltage. And but here the power loss at the fundamental frequency is considerably reduced. Means here the power loss is less, because this is the voltage here, the current which is flowing here is very minimum at the fundamental component. So, this value is less. In the damped filter here, it is the high pass filters, it is a low quality, the quality of factor is less. It's no sharp tuning is required. Only problem here, you have to tune this filter. Let's suppose this is your, we are tuning here for particular value, your impedance here, this is your ZF for a given frequency. If you are talking here, it will be tuned here. So this is basically, but in the band fault filter, it is nothing but its characteristic here, it is going like this. So it is basically the remaining it is passed, and here it is providing some pass here, and remaining it is reduced. So it reduces, also it reduces the transient voltage due to the high resistance in the circuit. Another here, the C type of filters can be used to reduce the loss. This is the more lossy. But if the C type of filters are used, then it will be, the loss will be reduced. Let us see the what is the C type and what is the configuration of this. You can see here, this is, as I said, here it is your single tuned RLC filter here, and you can say it is tuned for particular frequency, one frequency, where it is offering the minimum impedance, that is the resistance R, and so this is a RLC series circuit. Another, if you are going for the double tuned circuit, here we are having, this is a second order, this is here, and you can say this is providing the minimum impedance for the two frequency, that is F1 and F2. But your high pass filter, again it is a second order. You can see we are using here the C capacitors, here inductors, and is a resistor here. So this characteristic basically becoming like here. Now if you are using the C type of filter, what we do here, along with this inductor we put a capacitor, and that's why it is called the C type of filter. And this, what it does, it reduces the loss of the system, because here this is just parallel to this, and more current is flowing and more loss is there. So this filter is more lossy compared to this, so the C type of filters are used here. So that's why here I have written the C type of filters can be used to reduce the loss, because the normal here the damped filters, the losses are more compared to your tuned filters. Now the rating of the filter, how we'll define the rating of the filter. The rating of filters basically decided based on the three here. One is the highest power frequency of the AC voltage. What is this insulation level? If I can say this filter here is 66 kV, means this is its insulation level where it can be connected. So this is the power frequency voltage. If you are connecting here, so it is whatever the voltage here. So this is basically your phase voltage. It's not line to line, it is a phase voltage where we are talking. Then another is higher the effective frequency deviation, because if you are talking here, if you will see if frequency is varying, here we talk for particular frequency. If your frequency is your 50 hertz, if you are designing this filter for fifth harmonic, then it will be 250 hertz here. So in 250 hertz it is a minimum impedance, but if it is changing, this will also change. Means if this frequency is 49, then what happens, then you are not here, you are 49 into 5, you are somewhere here, then impedance is increased compared to here. So once it is frequency is deviation, we will see the detuning, it is called detuning, and we will define another term here, this is a delta for this detuning word, the change in the frequency deviation. And another is the highest harmonics content, means for which it is designed, means it is a fifth or seventh of it is, then it is also defined. Another criteria is also used, that how much reactive power it will provide to the system at the fundamental component. So it is in MVAR. We say this MVAR, this is a tuned filter for seventh harmonics. So that's why here I have written the size of filter is defined as the reactive power that the filter supplies at the fundamental frequency. So sometimes it's say it is 100 MVAR filter, seventh order, so we can say seventh it is a tuned, and its reactive power support at the fundamental is 100 MVAR or so. In this tuned filter design, what we do, we want that what will be the size and what will be the sharpness of the tuning, that is basically related to the quality factor of inductor. So here I have written the few things here, what is the changing, the power frequency may change, and also we can change L and C here due to the aging and the heating effect. To analyze this, let us consider the single order tuned filter, that is your RLC filter here. So we are considering here, this is your R and C here. This is a shunt filter. This is your resistance. Here your L and C. So total impedance at any frequency ZF can be written here your R plus J omega L 1 over omega C. We want to write this whole impedance, its characteristic, in terms of where it is tuned, for which frequency it is tuned. Means the tuning means where this imaginary value is 0, means this is this minus this is equal to 0. So that is called, it is the harmonics component for which it is designed, your n, I can say that frequency. So this value here will be equal to your under root LC as usual. Another term that is here delta, it is called the frequency deviation term. It is basically defined as omega minus omega n here divided by your omega n. This is also known as the detuning factor, or it is the deviation of frequency from the tuned frequency. This is your tuned frequency. So how much it is deviating? So it is defined, this is a factor where we normally draw it. So using this here, I can say this value is going to be your omega n. It is your how much? I can write here, this is this, it is going to be here, it is, I can say omega is your omega n 1 plus delta. So for any normal frequency here omega, this is your tuned frequency, and plus here 1 plus delta will be defined from here. Now I want to simplify this. I want to basically remove this L and C components, because L and C components may change, and we want to remove this. So we can also see your X naught, means X naught is the reactance, or it is a impedance when it is a tuned one. Means here I can say it is your omega n L. This will be equal to your 1 upon omega n into C, because at that time here this will be equal to this at the tuned frequency. What is this value of this X naught at that time? Now we can put this value here, this is R. We can also here put this value is equal to your L by is under root L by C. Just put this value here, you are going to get this. Okay. Now basically I want to replace this L and C, so I can say here it is your J. I can say it is your, just divide by here omega n, here by omega n, and multiplied by omega n. Basically what I am going to do here, instead of this, I want to write, take it out here. This is your J X naught, means I want to use this, I want to remove this L and C. What should be this?
In terms of this.
I want to remove this L and C. I want to either in X naught and omega n.
L equal to X naught by omega.
X naught by here?
Equal to X naught by omega. From that equation. In what is
I think I have written here, and this value will be we can take first R outside, or we can use in terms of quality factor also, we can use in this term also. So we can say here it is R 1 plus J omega L by R minus 1 by omega C into R. It is better to use in terms of quality factor. The quality factor Q is defined as omega n L over R, and also it will be equal to 1 over omega n C into R. Okay, so here I can write this is R 1 plus J, and here I can take the Q outside, it is your omega by omega n minus omega n by omega. Why I am doing this? Finally we will go for here in terms of this delta component. So this we can write here R 1 plus JQ. This will be your, we can replace from here. We are getting this value omega upon omega n. So we are getting 1 plus delta, and this is 1 over 1 plus delta. Now since this delta value is very, very small, then we can write our ZF is equal to your R 1 plus J Q 2 plus delta divided by 1 plus delta. No? Into delta will be there. That's true. Or approximately, if the delta is very, very small, I can say delta is very, very small this, then we can write this ZF will be equal to your R 1 plus J2Q delta. Q is the quality factor. Now if I can write this value is equal to your x into k term, I want to write here this value here ZF in this form. So what will be value of k? Because the figure which is I am showing here, it is in terms of k and here in terms of delta. This is the x naught is nothing but the x naught we write here. So we can write in the quality factor again, because this x naught here we can just write in terms of quality factor even for this example itself here. So tell me, this is x naught into k, what will be the value of k? Can we write something here in terms of this? Your x naught, we can take this value in terms of, again here it is, we can write your omega n L, but mind it, I don't want to use this L and C. In this simplification, I don't want this, R can be there, no doubt. What will be this value? Can we write something here in terms of x?
Q is x naught by R.
Q is
X naught by R.
x naught by R. Yeah. So it is very simple here. Means here what we are going to, k will be your 1 over q plus 2 delta j term here, or we can write here this term, this is your 2 plus delta, here 1 plus delta. So here we got this k is equal to this. Now you can see for the given value of your q factors, if q is your infinite, we are going to get this k value here, it is your 0, this will be 0, and we are going to have j delta 2 plus here delta by 1 plus delta. And you can see from here, if the delta is 0 here, then k is going to be 0, and this value is coming here. For other values here, if q is not here infinite, always we are adding some value here. Basically this is the mod, we are taking k mod here. If you are taking mod, so it will be going the both side. So now you can say if q quality factor is infinite, which is not possible, then we are getting this y term, otherwise it is shifting and some impedance, some k value is appearing. So, and also you can see this is a tuned filter, the quality factor is still it is very high. So that's why your tuned filters or shunt filters here the quality factor is very high. Another option here, that is we can go for the double tune filters, and double tune filters are basically for the two frequencies. Here I will come back here this derivation again. In this, the double tune filters are possibility. Let us suppose you are having one tune filters and another tune filter you can connect in the parallel, then it will be the two tuned. Like here you are having your resistance, here your inductance, and this is your capacitance, here the ground. I can say it is R1, L1 and C1. This is tuned for one frequency, and if you are having another impedance here, resistance here, and this is your, I can say R2, L2 and C2. If they are connected here the parallel here, then we can say it is a double tune filter. So there is no special thing here, but only we are having the two big inductors together, and these inductors are really sustaining the total voltage of the supply. But in actual double tune filters, we can have here, this is one is a resistor, this is a capacitor, here your inductor, here it is your resistor, and then we are having another capacitor, here resistance, and here we are having another capacitance and inductor. So this is a second order here, another double tune filter. In this case, what is happening, you are using only one inductor, here you are using the two inductors. So this is a single tune two filters, here single double tune filters are there. Basically what happens, this is more advantageous compared to here, because we are, this only one inductor is sustaining the complete voltage, and here also, so we are minimizing the cost. But no doubt we are putting some capacitors and the resistors here in the circuit, and if you will see the various advantage here, the two tune filter, as I said, they are connected in the parallel. So this is here, and we are having the single double tune filters here. The major advantage here in this, the loss is minimum, and also here one inductor is subjected to your full voltage, and the characteristic, you know, it is nothing but it is your the two tune filters here, the two frequency, it will provide the minimum path. And if you see this, its impedance diagram, that is your resistance and X, it is basically, it is coming all together like this. You are involving here this is your value, the minimum impedance is coming. Means you are getting the two impedances minimum for your, the two R's are here for one X. Now this delta term, why the delta we are using? The major function of this delta, because there is a possibility that there is a frequency change, and that frequency change is your operating frequency change, because this is your AC system frequency may change, and thereby your this frequency tuning will also change, because you may land here or here, that side, depending upon frequency is increasing or decreasing. So one factor here is the frequency change, and another due to the change of the elements of that tune filter itself, because this inductance may change, your capacitance may also change, especially the inductance and capacitance changes due to the aging or maybe due to the heating event. This value changes, no doubt the value change is very small, but it is still significant. So the change this delta is basically defined in terms of this. Now why this is happening like 1/2, and this is like here, what is your, this is defined as your omega minus omega n divided by omega. This is nothing but your omega by omega n, here minus 1. Your this omega n, here I can write this is your omega, this value is your C by L minus 1, because omega n we define here, this is a root L upon C. Now you can use this change term here, this term is the under root, that is why it is coming 1/2. So you can see this is change here, we can write the change in this frequency, that is change in omega by omega, plus this is under root 2, so then it will be 1/2. If it is a square term, this is twice is coming, and then this is by 2, so here del C upon C. Here term is coming negative, if you are differentiating here the partial differentiation, then it is your L upon C, but always the error if we take as a positive rather than negative. So this here the derivation comes from here, and you can say this is nothing but your f upon f. It's the same. If you are changing omega divided by omega is equal to change in frequency by frequency. So this change basically delta here we are defining this delta in this term. So this is the change here. So you can say if there is some change here, it is half of that change is coming into this delta, but the frequency change is directly reflecting here. That's why the frequency change is more prominent than the changing your C value or L value. And also in practice, this change is so frequent that compared to this change as well. Now another here we are going to I am going to show you how it is your, if this is a filter which is giving tune for any particular harmonics component, means it is providing the minimum impedance, whether its circuit is behaving like a capacitive circuit or reactive power it is providing at the fundamental frequency. You know this, let's suppose the current which is flowing here, it is your I. Means I1 I am talking for the fundamental component, and IH for which it is designed here which is flowing, it is designed for the tuning. Because it is having so many components, it is current is flowing because it is offering the impedance for all these components I1, I2, I3, whatever, although it is 0 I2, so I5, I7, I11 something, all the components. So I want to show that this reactive power Q is defined that your I1 square into this your this reactance here, your XL minus your XC. Okay, total here XL reactance sum minus this, because this effectively it is reducing. This is a reactive power which is total consumed or generated. We have to see it. Now this value XL we can write here is omega 1 is it's I1 square. Here is omega L minus 1 over omega C. Here I am writing 1 and 1 for the fundamental component. Means that will be equal to, I can say I1 square. Here this I can take omega 1 outside and even though L. This is the 1 minus here omega 1 square L into C. Right? And 1 upon LC here is omega n square. So I can write here it is I1 square omega 1 L 1 minus omega n omega 1 square. Okay, and this omega n is nothing but it is h times omega 1. So I can write here it is your I1 square omega 1 L 1 minus here this value is your, this is a cancel, it is I can say h square simply, because this omega here n it is your for which it is designed h into omega 1. So it is the fifth, so the 5 times of fundamental frequency. And you can see this value is always larger than unity, because we are designing for 5th, 7th, etc. So this value becomes negative. What does it mean? Means this is behaving as a capacitive. And you can see this is a huge amount. Now you can imagine this is a 5th component, so 25 minus 1, it is a 23 times of this component. So it is giving significant amount of reactive power support that is required to the system. So this is basically, we can see the shunt filters, especially not the series filter. Shunt filters provide the reactive power support at the fundamental component. However, the series, you can also prove for the series filter it is always consuming. You can just even also verify in the similar manner. So now another criteria that's we have to design the filter that it should be have the cost should be minimum. Normally the cost of the filters are 5 to 10% of the terminal equipment. Terminal equipment, I mean that we are having your converter, all other auxiliary transformer, your line, smoothing reactors, protection system, etc. The total terminal equipment, it is this filters cost basically 5 to 7%, because you know it is looking a very simple inductor. It is looking a very simple capacitor, but if you will see, this capacitor requires use of this room. The inductor you will see just like a bigger than a transformer, because the value of this inductor is required for the particular harmonics, 5th, 7th, etc. And as well as if you are going for higher and higher harmonics, the size of these filters becomes more and more larger. So why it is so? Now you can see this is omega n. We proved here your L upon C. If you are going for this larger value, you have to increase this value or you have to decrease this value. Decreasing the capacitance also, this is one issue because you are writing in series. Here inductance, the size of inductance value is more. So you are going for the larger and larger size of components, that is L and C, and the cost becomes very, very high. So that's why we go for only the lower order harmonics. If we are operating at the 6 pulse converters, then we go for 5th, 7th, 11th and 13th. If you are going for your 12 pulse converters, then we use the tune filters for 11 and 13, and remaining we can just either pass it to the system, or sometimes we can use the band pulse filter nearby that, so that it can be not going to the AC system. So in the total, I want to say that the cost of the filter is one criteria, and the cost is basically related that how much reactive power it is supporting. So the cost of the filter, total cost, there are some fixed cost, there are some cost related to your inductors and this C. So we'll see how we are going to get the optimal value of the minimum cost filter design, and we'll see that in the next lecture. So in the next lecture, what I'll discuss about the cost of the tuned filters, and also we'll see some consideration for the design of the band pass filters. Then the filter aspect will be over, and then later on we'll talk about this grounding and the line design. Then this module will be over. So 2 more lectures I'll be taking in this module, and then we'll finish it. After that we'll go for the power flow and other things. Thank you.